When humanity looks up at the night sky, it sees only a fraction of what is truly out there. For generations, astronomers relied on telescopes that could capture only the light visible to the human eye. These instruments revealed planets, stars, galaxies, and nebulae. But the deeper secrets of the universe remained hidden behind clouds of dust, vast cosmic distances, and the limitations of Earth-based observation. Everything changed with the launch of the James Webb Space Telescope, a mission that redefined the boundaries of what we could observe and understand. Webb's arrival marked the beginning of a new era, one in which the earliest galaxies, the atmospheres of distant planets, and the hidden details of worlds within our own solar system suddenly became accessible. If you're intrigued by the mysteries of distant moons and the potential for life beyond Earth, subscribe now. The James Webb Space Telescope is about to reveal what we've only dreamed of discovering. With its groundbreaking ability to peer through cosmic dust and unveil the secrets of hidden worlds, Webb's mission has already begun to change everything we thought we knew about our solar system and the universe beyond. The James Webb Space Telescope, commonly known as JWST, was conceived in the 1990 seconds as the successor to the Hubble Space Telescope. Engineers and astronomers envisioned a tool capable of studying the universe in infrared wavelengths, which are essential for seeing through cosmic dust and observing objects too faint or too distant for visible light telescopes. It took more than 2 decades of development to turn this vision into reality. The telescope cost approximately $10 billion, involved over 10,000 scientists, engineers, and technicians, and required collaboration among NASA, the European Space Agency, and the Canadian Space Agency. One of the defining features of the James Webb Space Telescope is its enormous primary mirror. With a diameter of 6.5 meters, it dwarfs the 2.4-meter mirror of Hubble. The mirror consists of 18 hexagonal segments made of beryllium and coated with a thin layer of gold, only a few hundred atoms thick. This gold coating optimizes the mirror for infrared reflection, allowing Webb to capture extremely faint signals from the early universe. Each hexagonal segment is equipped with actuators capable of adjusting its position with nanometer precision. The alignment process took months after launch, as engineers worked meticulously to calibrate every segment into a single, perfectly shaped optical surface. The size of the mirror presented one of the greatest engineering challenges. The mirror was too large to fit inside the rocket fairing used for launch, so it had to be folded up like a piece of intricate space origami. This folding also applied to the telescope's massive sunshield, a multi-layered structure roughly the size of a tennis court. Made of 5 layers of a material called kapton, the sunshield protects Webb's instruments from heat emitted by the sun, Earth, and even the telescope itself. Without this protective barrier, the telescope would be too warm to detect faint infrared signals, which require extremely cold temperatures. Once deployed in space, the sunshield allows Webb to maintain a temperature of around 233 degrees Celsius, cold enough for its instruments to observe the universe without interference from thermal noise. Another key element of Webb's design is its location. Unlike Hubble, which orbits Earth, Webb resides at the second Lagrange point, known as L2. Located around 1.5 million kilometers from Earth, L2 is a gravitationally stable point where the telescope can remain in alignment with our planet and the Sunday. From this vantage point, Webb avoids the constant transitions between sunlight and Earth's shadow that would complicate thermal management. The stable location provides uninterrupted access to deep space and allows the telescope to remain in a continuous communication link with mission control. Webb orbits around L2 in a halo orbit, ensuring that its view of the cosmos is never obstructed. When Webb launched aboard the Ariane 5 rocket from French Guiana on the 25th of December 2021, the world watched with anticipation. The deployment sequence involved more than 300 separate mechanisms, each needing to function flawlessly. Engineers described the process as the most complex deployment ever attempted in space. Over the course of 2 weeks, the telescope unfolded from its compact launch configuration into its full operational shape. First, the sunshield stretched out and tensioned its 5 layers one by one. Then the mirror's wings swung into position, and finally the fine adjustments began that would determine the telescope's optical performance. When the mirrors were fully aligned, tests confirmed that Webb was exceeding its original specifications. The deep field image revealed thousands of galaxies in a tiny patch of sky no larger than a grain of sand held at arm's length. Some of these galaxies existed more than 13 billion years ago, formed shortly after the Big Bang. The image displayed spiral galaxies, elliptical galaxies, merging galaxies, and distant red-shifted galaxies whose light had been stretched by the expansion of space. The clarity and depth of the image exceeded what Hubble had achieved, and the data provided a new resource for astronomers studying the early universe and galaxy evolution. But Webb was not designed only to look at ancient galaxies. Its instruments allow scientists to study the atmospheres of exoplanets, worlds orbiting stars, far beyond our solar system. By analysing the way starlight passes through a planet's atmosphere during transit, Webb can detect molecules such as water vapour, methane, carbon dioxide, and other gases. These readings provide essential information about planetary composition, temperature, and potential habitability. Early results included detailed spectra of several exoplanets, including WASP 96b, revealing complex atmospheric characteristics and demonstrating that Webb could identify molecular signatures with extraordinary accuracy. This level of detail is essential in the ongoing search for planets that might support life. The telescope also plays a role in studying objects within our own solar system. Its infrared capabilities allow scientists to observe planets, moons, and icy bodies with new clarity. Webb can detect heat patterns, characterize surface materials, and measure atmospheric components that were previously too difficult to observe. This capability helps for studying Jupiter's moons, including Europa, which has an icy shell covering a global ocean. Previously, observations were limited to flyby missions and telescopes that lacked the sensitivity needed to analyze Europa's surface and atmosphere in depth. Early observations of Europa revealed details suggesting possible activity beneath the ice. The telescope detected faint signatures that may indicate chemical interactions and potential plumes rising through cracks in the surface. These observations provided spectral data that allowed researchers to distinguish among different types of ice, salts, and some organic molecules. This capability enables more detailed study of interactions between the Moon's surface and its subsurface ocean. Ground-based instruments on Earth would not be able to collect such detailed infrared observations because Earth's atmosphere blocks many infrared wavelengths. Behind the scenes, an intricate team of scientists and engineers manages Webb's operations. More than 1,200 people work in mission control, data analysis, and maintenance operations. The Space Telescope Science Institute in Baltimore acts as the central hub for receiving and processing data. Teams of researchers around the world propose observation projects, competing for limited time on the telescope. Every second of Webb's observation schedule is carefully planned to maximize scientific return. Because Webb operates so far from Earth, it cannot be repaired or upgraded like Hubble. So each component must function reliably for the mission's expected lifespan of at least 10 years. though many researchers believe it could operate for 20. The launch of the James Webb Space Telescope marked a major technological advance in infrared astronomy. Webb provides observational capabilities beyond those of Hubble, improving our ability to study galaxy formation, stellar and planetary evolution, and conditions on distant planets and solar system bodies. Its observations extend from distant galaxies to icy moons in our solar system, such as Europa. Jupiter's moons, the hidden worlds of our solar system. Jupiter has always held a unique place in the story of our solar system. With a diameter of more than 139,000 kilometers, it is large enough to fit more than 1,300 Earths inside it, and its gravitational influence stretches across millions of kilometers. But while Jupiter itself has fascinated astronomers for centuries, it is the worlds that orbit it, its moons, that have become some of the most intriguing objects ever studied. More than 95 moons have been identified around Jupiter, ranging from tiny irregular fragments only a few kilometers wide to massive worlds larger than planets like Mercury. Among these moons lie environments so varied and complex that they form a planetary system of their own. As scientists continue to explore these worlds, it becomes increasingly clear why Jupiter's moons are considered prime locations for discovering the most profound secrets of our solar system. Long before the James Webb Space Telescope turned its gaze toward Jupiter's orbit, astronomers had already studied the planet's 4 largest moons: Io, Europa, Ganymede, and Callisto. These moons, known collectively as the Galilean moons, were discovered in 1610 by Galileo Galilei using one of the earliest telescopes ever constructed. The moons moved in predictable patterns around Jupiter, providing early observational evidence that not all celestial bodies orbit Earth. The Galilean moons are active worlds with complex geologies, atmospheres, and, in some cases, oceans beneath icy crusts. Each moon exhibits unique physical processes, and the diversity among them provides insight into the range of planetary conditions that exist in the solar system. Io, the innermost of the Galilean moons, is roughly the same size as Earth's moon and is in constant geological activity. More than 400 active volcanoes have been identified on its surface. Some eruptions send plumes of sulfur and other gases more than 300 kilometers into space. The heat driving this activity comes from tidal forces exerted by Jupiter and gravitational interactions with Europa and Ganymede. As Io orbits, it is stretched and compressed, generating internal friction that melts portions of its interior, fueling volcanic eruptions. Scientists use high-resolution infrared observations to track these eruptions, which can reach temperatures exceeding 1,000 or 600 degrees Celsius. Europa's surface temperature averages around -160 degrees Celsius. Beneath its icy shell lies a global subsurface ocean that may contain more than twice the volume of water found in all of Earth's oceans combined. The existence of this ocean was first suggested by data from the Voyager missions in the late 1972 and later confirmed by the Galileo spacecraft in the 1992. Hydrothermal vents may exist on Europa's ocean floor, similar to those found on Earth, which could provide chemical energy sources for potential biological processes. Beyond Europa lies Ganymede, the largest moon in the solar system, with a diameter of more than 5,200 kilometers. It is larger than Mercury, though less dense. Ganymede is the only known moon with a magnetic field, first discovered by the Galileo spacecraft, suggesting a partially liquid iron or iron sulfide core. Its surface shows darker regions covered in impact craters and lighter areas with grooves and ridges indicating past tectonic activity. Scientists also hypothesize that Ganymede may host multiple layers of oceans, separated by layers of ice, possibly containing more water than Europa, but distributed differently. Callisto, the outermost of the Galilean moons, is one of the most heavily cratered objects in the solar system. Its surface preserves evidence of impacts dating back billions of years, providing a geologic archive with little resurfacing. Data from the Galileo mission indicated that Callisto may also harbor a subterranean ocean, suggesting that 3 of the 4 largest moons of Jupiter contain substantial quantities of liquid water in varying geologic environments. Interactions among Io, Europa, and Ganymede create a phenomenon known as orbital resonance. For every orbit Ganymede completes, Europa completes 2 and Io completes 4. This arrangement maintains gravitational forces that drive tidal heating and sustain internal activity within each moon, influencing their geologic and oceanic processes. Over the past 50 years, several missions have provided data about these moons. The Pioneer and Voyager missions gave the first close-up images. The Galileo spacecraft, launched in 1989, conducted multiple flybys of the Galilean moons. The Juno spacecraft, which arrived at Jupiter in 2016, provided detailed images and measurements of Jupiter's magnetosphere and the behavior of charged particles around the moons. In 2023, the European Space Agency launched the Jupiter Icy Moons Explorer, or JUICE, which will conduct investigations of Ganymede, Europa, and Callisto in the 2030 seconds. Jupiter likely formed early in the solar system's history, attracting gas and dust as it grew. Around the forming planet, a disk of material created the building blocks for the moons, similar to the way planets formed around the Sunday. Observations show that moons like Ganymede and Callisto may have captured material from different regions of the early solar nebula, preserving chemical signatures that provide information about ancient conditions. Scientists continue to investigate mechanisms that keep Europa's ocean liquid, the age of Ganymede's deep oceans, and whether volcanic activity on Io affects chemical processes on Europa or Jupiter's magnetosphere. These topics guide observation priorities for next-generation observatories like the James Webb Space Telescope. The James Webb Space Telescope observes infrared wavelengths, allowing scientists to study the composition of the moon's surfaces, detect heat signatures, and analyze atmospheric components with high precision. These capabilities help identify chemical compounds on Europa that may originate from its ocean, detect heat from surface features that could indicate subsurface activity, and observe interactions between Jupiter's magnetic field and the moon's. Observations have revealed anomalies, prompting further investigation into Europa's environment. Jupiter's moons exhibit a range of geologic and environmental diversity, including layers of ice, volcanic activity, and tidal effects from Jupiter's gravity. Observations from Webb continue to focus on Europa, where data is being collected on surface composition, potential subsurface activity, and interactions with Jupiter's magnetic field. Europa, the ice moon that might harbor life. Among the many moons orbiting Jupiter, Europa stands out as one of the most enigmatic and scientifically compelling. Slightly smaller than Earth's moon, with a diameter of 3,121 kilometers. It is an icy world that conceals a global ocean beneath its frozen crust. The notion that a moon so far from the Sun could host a vast, potentially habitable environment challenges traditional ideas about where life might exist and reshapes the way scientists approach the search for life beyond Earth. Unlike the volcanic fury of Io or the heavily cratered surface of Callisto, Europa presents a delicate balance of frozen surface, liquid water, and potential chemical energy, an environment that makes it one of the most promising targets for astrobiology in the solar system. Observations of Europa date back to the late 19th century, when astronomers noticed irregularities in its surface albedo, or brightness. In 1979, the Voyager missions provided detailed images of its surface, revealing a smooth, bright ice sheet with intersecting cracks and ridges, far less cratered than expected for a body billions of years old. Europa's surface is estimated to be 40 to 90 million years old, suggesting ongoing internal processes. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, detected variations in Europa's gravitational field, indicating a subsurface ocean beneath a shell of ice, approximately 15 to 25 kilometers thick. This ocean likely covers the entire Moon and is in contact with a rocky mantle. Heat from tidal flexing caused by Jupiter's gravity keeps the ocean from freezing, despite average surface temperatures of around -160 degrees Celsius. Models suggest the ocean may reach depths of 60 to 150 kilometers, potentially containing more than twice the volume of Earth's oceans. Europa's ice sheet is interrupted by long linear features called lineae, some stretching thousands of kilometers. These cracks reflect stresses from tidal forces and may allow material from the subsurface ocean to reach the surface. Darker regions, called chaos terrains, appear to be disrupted ice plates that have moved or rotated. Certain areas display reddish-brown streaks, which may be salts, sulfur compounds, or organic materials carried upward from the ocean below. Studying the composition of these materials provides information about the Moon's geochemistry and internal processes. Europa has a tenuous atmosphere composed primarily of oxygen, with a surface pressure of about 1/1000th of Earth's atmosphere. High-energy particles trapped in Jupiter's magnetic field collide with Europa's icy surface, causing water molecules to split into hydrogen and oxygen. The molecular oxygen may interact with the ocean beneath the ice, influencing the Moon's chemical processes. Observations from the Hubble Space Telescope suggest intermittent plumes of water vapor rise through Europa's ice, reaching heights of up to 200 kilometers above the surface. These plumes could carry salts, organic molecules, and other chemical signatures from the subsurface ocean. Detecting these materials requires instruments sensitive to ultraviolet and infrared light, such as the James Webb Space Telescope. Spectroscopic studies indicate that Europa's ice contains water as well as salts, such as magnesium sulfate, sodium chloride, and possibly carbonates. These substances may originate from interactions between the ocean and the rocky mantle beneath, which could provide chemical energy. Hydrothermal activity on Earth relies on chemical gradients independent of sunlight, and similar processes may exist in Europa's ocean. Europa exhibits magnetic anomalies that suggest a conductive layer beneath its ice, consistent with a salty, global ocean. Measurements from the Galileo spacecraft detected variations in the Moon's induced magnetic field as it moved through Jupiter's magnetosphere. These variations indicate that the ocean is rich in dissolved salts, which enhance its conductivity. Tidal heating plays a significant role in Europa's internal processes. As Europa orbits Jupiter, gravitational forces from both the planet and neighboring moons create friction within its interior, generating heat. This heat helps maintain the liquid state of the ocean and may drive geological activity on the sea floor, including volcanic or hydrothermal processes. Exploring Europa is challenging due to its extreme environment. Surface temperatures are very low, radiation levels are high from Jupiter's magnetosphere, and the thick ice crust limits access to the subsurface ocean. Several missions are planned to investigate Europa in detail, including NASA's Europa Clipper, which will conduct flybys to map the surface, analyze the ice and atmosphere, and measure magnetic fields and ice thickness. The European Space Agency's Jupiter Icy Moons Explorer will also study Europa from orbit, providing additional data on its geology and ocean characteristics. The potential for habitability on Europa is supported by comparisons to extreme environments on Earth. Microbial communities thrive in Antarctic subglacial lakes, deep-sea hydrothermal vents, and other isolated environments, demonstrating that life can persist under extreme cold, high pressure, and limited sunlight. Europa's ocean may replicate similar conditions, providing a natural laboratory for studying life in extreme environments. Its thick ice shell offers protection from cosmic radiation, while chemical energy from interactions with the rocky mantle or oxidants produced at the surface may support microbial life. Europa provides insights into planetary formation, icy moon geophysics, and tidal heating dynamics. Its surface features allow scientists to examine how ice behaves under stress, while its ocean provides clues about the chemical and physical properties of large bodies of water outside Earth. Europa serves as a natural laboratory for studying interactions between planetary magnetospheres and moons. Jupiter's intense magnetic field generates radiation belts that influence surface chemistry, create sputtering effects, and modify the chemical composition of the ice. Studying these processes helps scientists interpret observations from exoplanets and their moons, where similar interactions may occur. Recent observations using advanced instruments show variations in ice composition across Europa's surface, with some regions enriched in salts, while others are dominated by pure water ice. Thermal anomalies detected in specific lineae suggest heat is being transported from below, indicating active geological processes. These findings suggest the ice shell's thickness may vary, and that surface disruptions could be driven by subsurface activity. Europa's frozen surface conceals a vast ocean, with cracks revealing dynamic geological activity. Its interaction with Jupiter's gravity creates a balance of forces that sustain its environment. As exploration continues, and advanced telescopes like the James Webb Space Telescope focus on this icy moon, Europa will provide further insights into its geophysical processes and potential for habitability. Webb's first look, peering beneath Europa's icy shell. The James Webb Space Telescope had already revolutionized astronomy by peering deep into the universe and studying distant exoplanets. But its observations of Europa presented an entirely new frontier. Europa, long suspected to hide a vast ocean beneath its icy shell, had been studied primarily through flybys and remote sensing from Earth-based telescopes and earlier spacecraft like Galileo. Webb offered something different: the ability to analyze the moon's surface and near-surface features with unprecedented infrared precision, allowing scientists to examine chemical compositions, thermal anomalies, and potential signs of activity that had never been seen before. The first Webb data on Europa arrived in late 2023, immediately sparking excitement and raising questions that challenged previous assumptions. Webb's infrared instruments operate in wavelengths from about 0.6 to 28 micrometers, enabling them to detect thermal emissions and chemical signatures that are invisible to the human eye. This capability is important for Europa, where surface temperatures rarely exceed -160 degrees Celsius. Small variations in heat across the ice can reveal subsurface activity or areas where the ice is thinner. Webb's near-infrared spectrograph captured spectral data of surface compounds with high detail. Early results identified water ice, various hydrated salts, and traces of sulfuric acid. These compounds suggest interactions between the surface and the subsurface ocean, indicating that material from below may occasionally reach the surface, potentially through fractures or cryovolcanic processes. Webb's initial observations detected localized thermal anomalies along Europa's lineage. These anomalies indicate regions where heat from below is reaching the surface, raising temperatures by 2 to 5 degrees above surrounding areas. These temperature differences, significant for Europa, suggest that the ice may be thinner in these regions. The presence of thinner ice layers increases the likelihood that oceanic material could escape to the surface, or that future missions might access the ocean through natural fractures. Webb's data provided the first concrete evidence of active thermal dynamics. In addition to thermal mapping, Webb revealed compositional variations across the Moon's surface. Spectral analysis showed that certain reddish-brown regions, previously assumed to be uniform, are actually complex mixtures of salts, sulfur compounds, and possible organic molecules. These materials are concentrated along fractures and chaos terrain, suggesting they may originate from the subsurface ocean. The distribution of these compounds also suggests interactions with Jupiter's radiation belts, which bombard the Moon's surface with high-energy particles. Webb's observations indicate that radiation may drive chemical transformations, converting simple salts into more complex molecules. Webb's observations indirectly detected potential plume activity. While Hubble had observed occasional water vapor plumes reaching hundreds of kilometers above the surface, Webb's infrared sensors detected localized emissions consistent with these features. Spectral data suggested the presence of water vapor and trace compounds such as carbon dioxide and hydrogen peroxide near the suspected plumes. If confirmed, these plumes provide an opportunity to study Europa's subsurface ocean remotely, without drilling through kilometers of ice. This capability is important for future missions like Europa Clipper, which could fly through these plumes and directly sample material from the ocean below. Webb's observations also shed light on the interaction between Europa and Jupiter's magnetosphere. High-energy particles trapped in Jupiter's magnetic field strike the Moon's surface, creating sputtering effects that release atoms and molecules into a tenuous atmosphere. By measuring the infrared emission from these interactions, Webb provided insights into the spatial distribution of oxygen, hydrogen, and other molecules in Europa's exosphere. Understanding how material is transported from the surface into the thin atmosphere helps interpret potential signs of habitability and informs models of how radiation affects the chemical inventory of the surface and near-surface regions. Webb's high-resolution spectroscopy revealed shifts in ice crystal structure across Europa's surface. Differences in grain size, crystallinity, and molecular orientation correlate with both age and geological activity. Younger, more recently resurfaced areas showed larger, more uniform crystals, while older regions exhibited smaller, more fractured crystals. These observations provide evidence of internal processes and may help scientists estimate the frequency of ice movement, the thickness of the ice shell, and the potential for ocean surface material exchange. Infrared imaging also allowed Webb to detect variations in surface albedo that correspond to underlying structures. Some areas, previously thought to be homogeneous, revealed subtle topographical features such as ridges, domes, and troughs that suggest tectonic stresses and cryovolcanic activity. These features suggest that Europa's ice shell is a dynamic surface influenced by both internal heat and external gravitational forces. The detection of such features helps refine models of Europa's geology, including the potential for fracture propagation that could connect the ocean with the surface. Webb's instruments also provided detailed analysis of minor surface constituents. Trace amounts of magnesium sulfate, sodium chloride, and possibly carbonates were identified, alongside more complex, organic-like compounds. These findings suggest that Europa's ocean is chemically active, interacting with the rocky mantle below and exchanging materials with the ice shell. Similar chemical gradients occur at hydrothermal vents on Earth, where life thrives in complete darkness, independent of sunlight. Webb's observations suggest that Europa could host analogous environments. Webb's data also revealed temperature differences along small-scale surface fractures. These microthermal anomalies, only a few kilometers across, indicate active processes at fine spatial scales. The observations suggest that localized tidal stresses may concentrate heat in specific regions, potentially creating pathways for liquid water to reach the near-surface environment. Webb's observations have impacted the planning of future missions. Data on thermal hotspots, plume locations, and surface composition provide guidance for Europa Clipper's flyby trajectory, instrumentation priorities, and target areas for in-depth study. The identification of regions with thinner ice or active chemistry allows scientists to prioritize sites for further exploration. Webb's observations raised questions about Europa's evolution. Variations in surface composition and ice structure suggest a more dynamic geological history. Certain lineae appear to be much younger than surrounding terrain, indicating episodic resurfacing events. The reddish-brown compounds along fractures may record a history of chemical alteration, providing clues about the long-term stability of the ocean and its chemical environment. Webb's observations provide tools for locating environments where life might exist. By identifying areas where chemical ingredients from the ocean might reach the surface, detecting plume activity, and mapping thermal anomalies, scientists can target locations for future exploration. While direct detection of life remains elusive, Webb's data helps identify sites where life, if it exists, may be found. A surprising signal, what Webb found on Europa. The James Webb Space Telescope had already redefined our understanding of distant galaxies, exoplanets, and stellar nurseries. But it wasn't just far-off worlds that captured its gaze. Closer to home, Webb's observations of Europa, a moon of Jupiter, would soon unravel surprises that would alter our perceptions of this icy satellite. In particular, one discovery from Webb's infrared observations would create a ripple throughout the scientific community as researchers detected an anomaly that could have profound implications for the search for life beyond Earth. In late 2023, after several months of data collection, Webb's instruments revealed an unexpected signal emanating from Europa's surface, unlike anything previously detected. The anomaly came from a region on Europa's icy shell where a network of fractures and ridges suggested possible subsurface activity. It was distinct from the usual thermal emissions, chemical compositions, or spectral fingerprints scientists had come to expect. The signal, detected by Webb's near-infrared spectrograph, or NIRSPEC, revealed an unusual chemical signature not previously associated with Europa's surface materials. Webb's sensors identified a concentration of organic molecules, compounds containing carbon, hydrogen, oxygen, and nitrogen that were more complex than simple carbon-based molecules like methane or carbon dioxide. The composition suggested a more complex chemistry than the simple icy compounds typically expected on Europa. The key finding was the presence of nitrogen-containing organics, potentially similar to amino acids or other fundamental building blocks of life. For years, scientists had theorized that Europa's subsurface ocean might harbor the necessary ingredients for life, such as water, chemical energy, and organic compounds. Until Webb's discovery, the presence of these compounds had only been suggested through indirect evidence, like salts and simple molecules found on the surface. The detection of complex organic molecules provided further evidence that Europa's ocean might be chemically rich and biologically promising. The signal was not just limited to the identification of organic molecules. Webb also detected subtle variations in the region's thermal emissions, suggesting geothermal activity originating from below the surface. These variations, though small, indicated that heat likely from tidal friction was rising to the surface in a way that had not been observed before. This heat could be the result of localized cryovolcanism, where icy materials, possibly mixed with salts or other compounds, were expelled from the subsurface ocean. These eruptions could provide pathways for ocean water to interact with the surface, carrying important chemical signatures along with it. Europa has long been considered one of the most promising places in the solar system to find microbial life. Earlier spacecraft missions, including Galileo, had provided evidence of a subsurface ocean. Webb's findings suggested that the ocean might be warmer and more chemically diverse than expected, and it could also be more dynamic. The organic molecules detected could serve as a foundation for life, similar to the role organic compounds play in the chemistry of life on Earth. These compounds could fuel microbial life, particularly if geothermal activity provides the necessary energy for metabolism. Webb's data suggested that these organic compounds might be linked to water plumes previously detected by the Hubble Space Telescope. These plumes, thought to be geysers of water vapor and other materials erupting from Europa's icy surface, could be carrying material from the subsurface ocean to the surface and beyond, offering an opportunity to study Europa's hidden depths. Webb's detection of organic molecules in the plumes suggested that these eruptions could carry biochemical signatures that are important for understanding the Moon's potential for habitability. If confirmed, these plumes could offer the first direct evidence of ocean material without having to land on the surface or drill through miles of ice. What made Webb's discovery remarkable was its ability to pinpoint the location and composition of the organic molecules with precision. The anomaly was concentrated in a region of Europa's surface where cracks and ridges were evident, suggesting that material from the subsurface ocean might be escaping through these fractures. This region, near Europa's equator, has been identified as one of the most geologically active areas of the Moon. Webb's findings indicated that this activity could be a pathway for material from the ocean to the surface. The complex organic molecules detected by Webb may have originated in the ocean, shaped by the conditions of Europa's icy shell and subsurface environment. On Earth, complex organic molecules are fundamental to the chemistry of life. From amino acids to nucleotides, these molecules form the building blocks of proteins, DNA, and other essential structures. While the detection of these compounds on Europa does not directly indicate the presence of life, it suggests that the Moon could be a more hospitable environment for life than previously understood. The discovery indicates that Europa's ocean may be chemically active and rich in organic materials capable of supporting biochemistry that could potentially support microbial life. This finding supports the hypothesis that Europa's ocean could harbour environments similar to those found on Earth's ocean floor, where life thrives in extreme conditions. On Earth, deep-sea hydrothermal vents, where hot water from beneath the Earth's crust meets the cold ocean, are home to ecosystems that rely on chemical energy rather than sunlight. Europa's subsurface ocean, with its heat sources, organic compounds, and water, could harbour similar conditions. Webb's observations suggest that Europa's ocean may be more dynamic and chemically diverse than previously thought, creating conditions where liquid water, chemical energy, and organic molecules could interact in ways similar to Earth's extreme environments. Webb's discovery marked a significant advancement in the study of Europa. While past missions had suggested the presence of an ocean beneath the ice, Webb's detailed observations provided concrete evidence that the Moon's ocean is chemically active, dynamic, and possibly capable of supporting life. The detection of complex organic molecules and geothermal activity indicated that the ocean beneath Europa is not just a stagnant, frozen environment, but one that may contain the ingredients needed for life. The discovery set the stage for future missions to Europa, particularly NASA's Europa Clipper, scheduled to launch in the mid-2022. Webb's findings will guide the mission's trajectory and help scientists prioritize which areas of Europa to explore in more detail. The Europa Clipper spacecraft will carry instruments designed to study Europa's surface and subsurface, including the detection of organic compounds, the analysis of plumes, and the measurement of ocean properties. Webb's observations have provided scientists with a clearer understanding of where to focus their efforts in the search for signs of life on Europa. Europa's atmosphere, unlocking clues to its hidden world. In the continuing saga of the James Webb Space Telescope's exploration of Europa, the Moon's atmosphere emerged as a key area of focus. While Europa's icy shell had long been the primary target for researchers, the Moon's tenuous atmosphere, also known as its exosphere, was equally important to understanding its potential for habitability. Scientists had previously detected traces of oxygen in Europa's atmosphere, but Webb's unprecedented sensitivity brought this delicate layer of gases into sharper focus, revealing a surprising complexity that could significantly influence our understanding of Europa's hidden world. Europa's exosphere is not an atmosphere in the conventional sense. It is an extremely thin, almost non-existent layer of gas, with a surface pressure about 1 billion times weaker than Earth's. Despite its faintness, Europa's exosphere plays a role in the overall dynamics of the Moon, especially considering its interaction with the surface, subsurface ocean, and Jupiter's powerful magnetosphere. The exosphere is primarily composed of oxygen, and scientists believe this oxygen is produced through interactions with Jupiter's intense radiation environment. Webb's ability to observe Europa in infrared wavelengths enabled the detection of faint but significant spectral signatures from the exosphere. In addition to oxygen, Webb's observations revealed that Europa's exosphere contains small amounts of hydrogen, sulfur, and even trace amounts of carbon dioxide. These elements suggest that the atmosphere is a dynamic system influenced by both surface and subsurface processes. The detection of oxygen in Europa's atmosphere is not new. This finding was first observed by the Galileo spacecraft in the late 1990s. However, Webb's observations provided a more detailed and nuanced picture. The oxygen in Europa's atmosphere is created through a process called radiolysis, in which high-energy particles from Jupiter's magnetosphere break apart water molecules on the Moon's surface. When water ice is bombarded by charged particles, the H2O molecules split into hydrogen and oxygen. While the hydrogen is lost to space, the oxygen remains, accumulating in the exosphere. This process is a result of Europa's interaction with Jupiter's radiation field, which can strip away lighter elements like hydrogen, leaving behind the heavier oxygen. Webb's observations uncovered more than just oxygen. One of the most intriguing findings was the presence of sulfur compounds, which had not been detected in significant quantities before. These compounds, possibly sulfur dioxide or sulfuric acid, could be the product of interactions between Europa's surface and Jupiter's powerful radiation. Similar sulfur compounds are seen on other moons of Jupiter, such as Io, where volcanic activity is responsible for the production of sulfur-rich gases. Europa, with its icy surface and lack of active volcanoes, was not expected to show such rich sulfur chemistry. This discovery indicates that Europa's surface is chemically active and that its exposure to Jupiter's radiation may be driving complex chemical reactions. The sulfur compounds detected by Webb are significant because they provide clues about the ongoing chemical evolution of Europa's surface. These compounds are likely formed through a process called radiolysis, where radiation from Jupiter's magnetosphere causes the breakdown of surface materials, especially sulfur-rich compounds that may be mixed into Europa's ice. This process indicates that the surface chemistry of Europa is actively changing over time due to the radiation environment. Europa's exosphere is not just a byproduct of the Moon's icy surface. It plays a role in understanding the chemical pathways that could support prebiotic chemistry. The most surprising result from Webb's infrared observations was the detection of trace amounts of carbon dioxide in Europa's exosphere. Carbon dioxide is involved in many biological processes, and its presence on Europa suggests ongoing chemical reactions on the Moon's surface that involve carbon-based compounds. This finding suggests that Europa's environment could be more chemically complex than previously thought. The composition of Europa's atmosphere provides valuable clues about the interactions between its surface, ocean, and Jupiter's radiation. These findings indicate a more complex environment on Europa than previously understood. Rather than being a simple frozen world, Europa appears to be an active moon with chemical exchanges between its surface and subsurface ocean. Webb's ability to study Europa's exosphere is especially remarkable because it provides insights into the processes that shape the Moon's surface and atmospheric environment. For instance, the sulfur compounds detected could be the product of chemical reactions involving water ice, salt, and sulfuric acid. These compounds could also provide a window into the internal dynamics of Europa's ocean, as interactions between the ocean and the icy shell could produce volatile compounds that are subsequently released into the exosphere. Understanding these processes is important for determining how Europa's surface and ocean interact. The exosphere of Europa raises new questions about the nature of the Moon's atmosphere and the factors that influence its composition. The interaction between Europa's surface and Jupiter's magnetosphere is a key driver of these processes. Jupiter's magnetic field bombards Europa's surface with high-energy particles, causing chemical transformations. These interactions play a role in shaping the chemistry of Europa's ice and its exosphere. Webb's observations are the first step in unraveling this complex relationship, which will help scientists refine their models of Europa's atmospheric chemistry. Another important aspect of Europa's exosphere is its role in the broader dynamics of the Moon's environment. Europa's tenuous atmosphere is influenced by its interaction with Jupiter's radiation field, as well as the tidal forces generated by its orbital resonance with the other Galilean moons. These forces create friction within Europa's interior, driving geological activity beneath the ice shell and influencing the movement of materials between the surface and subsurface ocean. The exosphere is an active system that provides insights into the processes shaping Europa's geology and chemistry. Webb's data on Europa's exosphere has begun to shape future exploration plans. By identifying key compounds in the atmosphere, Webb has helped scientists prioritize areas for future missions, such as the Europa Clipper, which is set to launch in the coming years. This spacecraft will study Europa's surface, subsurface, and exosphere in more detail, allowing researchers to build on Webb's findings and further investigate the Moon. The discoveries made by Webb will guide the trajectory of these future missions, helping to focus attention on the most promising regions for further study. The combination of Webb's advanced infrared capabilities and the upcoming Europa Clipper mission means that the coming years will see a surge of new data about this moon. Webb's observations of Europa's atmosphere have already provided key insights into its chemical composition, but much remains to be discovered. As scientists continue to analyze Webb's findings, they will refine their understanding of Europa's exosphere, its interaction with Jupiter's radiation, and its surface processes. Europa's ocean. What the data tells us about its depths. As the James Webb Space Telescope continues to unveil the mysteries of Europa, one of the most compelling aspects of its exploration has been its ability to provide new insights into the depths of the Moon's subsurface ocean. Europa's ocean has long been a focal point for researchers, who have speculated that beneath the icy shell lies a vast, liquid water ocean, an environment that could potentially harbour life. While early missions, such as NASA's Galileo spacecraft, provided evidence of an ocean beneath Europa's frozen surface, it was Webb's advanced infrared capabilities that allowed scientists to begin unravelling the true nature of this mysterious ocean in greater detail. Europa's ocean is unique in that it is buried under an icy shell that ranges in thickness from 10 to 30 kilometres, making direct access to the liquid water beneath nearly impossible without specialised technology. However, through Webb's observations, scientists were able to gather indirect evidence of the ocean's characteristics, shedding light on its depth, composition, and structure. The depth of Europa's ocean has long been a topic of speculation, with previous models suggesting it could be anywhere from 50 to 150 kilometres deep. Webb's data, however, brought new clarity to the issue, suggesting that the ocean could be even deeper than once thought, possibly extending to depths of up to 200 kilometres in certain regions. One of the most striking findings from Webb's observations was the detection of thermal anomalies along the Moon's surface. These thermal features suggest that heat is being transferred from the subsurface ocean to the surface. The presence of heat at Europa's surface has been attributed to tidal heating, a phenomenon caused by the gravitational interaction between Europa and Jupiter's other moons, particularly Io and Ganymede. These tidal forces stretch and compress Europa's interior, generating friction and heat. Webb's infrared observations of thermal hotspots on Europa's surface confirmed that this process is ongoing and could be driving significant geothermal activity beneath the icy shell. This heating could help sustain the subsurface ocean, keeping it warm enough to remain liquid despite the extreme cold of Europa's surface. The heat being generated within Europa's ocean could also have significant implications for the Moon's environment. On Earth, hydrothermal vents where warm water from beneath the Earth's crust meets the cold ocean serve as rich ecosystems, supporting unique life forms that rely on chemical energy rather than sunlight. Europa's ocean could harbour similar environments, where microbial life might thrive in the warmth of the ocean floor. Webb's detection of these thermal anomalies further strengthens the case that Europa's ocean could provide the necessary conditions for sustaining complex chemistry. The ocean's depth, along with its geothermal activity, makes Europa an interesting place for astrobiological exploration. Webb's observations also provided valuable information about the composition of Europa's ocean, specifically its salinity. Webb's data, in combination with previous measurements from the Galileo spacecraft, suggests that Europa's ocean is salty, with concentrations of salt comparable to Earth's oceans. This is significant because a salty ocean would be more chemically active than a freshwater ocean, increasing the likelihood of interactions between water and minerals. Salts such as sodium chloride and magnesium sulfate have been detected on Europa's surface, and Webb's infrared spectroscopy provided the first evidence that these salts could be present in the ocean beneath the ice. The composition of Europa's ocean also points to a rich, dynamic chemistry. Webb's infrared data revealed the presence of organic compounds on the surface, including carbon-based molecules that could serve as the building blocks of life. These compounds could be transported from the ocean to the surface through cracks in the ice or via water plumes. While Webb's instruments could not directly sample the ocean itself, the detection of organic molecules and salts suggests that the subsurface ocean is chemically active. The presence of salts and organic compounds in Europa's ocean also raises the possibility of a subsurface biosphere, an ecosystem that could be sustained by geothermal energy and chemical reactions rather than by sunlight. Just as life on Earth thrives around hydrothermal vents, life on Europa could survive in a similar environment. The combination of water, heat, and organic chemistry provides the fundamental ingredients for life, and Webb's findings suggest that Europa's ocean may offer these conditions. These discoveries are important because they shift the focus of the search for extraterrestrial life beyond just the surface of Europa. The subsurface ocean is now a primary target for future missions. As Webb's data continues to refine our understanding of Europa's ocean, it also raises new questions about how this ocean might interact with the icy shell above. The ocean's depth and salinity are influenced by the thickness and composition of the ice, which in turn is shaped by tidal heating and interactions with Jupiter's radiation environment. Webb's thermal observations of the surface provided important clues about the relationship between the ocean and the ice shell. In some regions, the heat signatures detected by Webb suggested that the ice shell could be thinner than previously thought, allowing for greater fluid exchange between the ocean and the surface. This would increase the likelihood of material from the ocean being transported to the surface and venting into space via the plumes detected in earlier observations. The interaction between Europa's ocean and its ice shell is also crucial for understanding the Moon's long-term dynamics. Scientists believe that Europa's ocean could be chemically separated from the surface by a thick ice crust, but Webb's data suggests that this crust may not be as impermeable as once believed. Webb's ability to detect subtle thermal variations across the surface of Europa has provided new insights into the dynamics of the Moon's ice shell, indicating that heat from the ocean could be driving more active exchanges between the subsurface and surface. This interaction could help maintain the chemical balance of the ocean. The discovery of heat and salinity gradients within Europa's ocean, as well as the presence of organic compounds, also has important implications for the upcoming Europa Clipper mission. Set to launch in the mid-2022, Europa Clipper will conduct detailed flybys of the Moon, gathering data on the composition of its ocean, its ice shell, and the surface features that Webb has already revealed. Webb's observations will help guide the trajectory of the Europa Clipper mission, focusing attention on the most promising regions of the Moon for further exploration. By combining Webb's data with the detailed measurements from Europa Clipper, scientists will be able to refine their models of Europa's ocean. Europa's ocean is a place of tremendous scientific interest, offering insights into the conditions beneath Europa's icy surface. Webb's observations have provided a wealth of information about the ocean's depth, temperature, salinity, and chemical composition. These findings point to the possibility of a dynamic and chemically active environment beneath Europa's icy surface. As scientists continue to analyze Webb's data and prepare for future missions, Europa's ocean remains a key target in the search for life beyond our planet. Webb's exploration of Europa's ocean has provided new insights into the Moon's subsurface environment. The combination of heat, water, salts, and organic molecules points to a dynamic and chemically active ocean beneath Europa's icy surface. As we move forward in the exploration of Europa, Webb's discoveries will serve as a foundation for future missions, helping to refine our understanding of the Moon's geophysical and chemical processes. Europa's surface features. What lies beneath the ice? As the James Webb Space Telescope continues to explore Europa, it reveals not only the chemical and thermal properties of the Moon's subsurface ocean, but also the intriguing surface features that offer critical clues about the dynamic relationship between Europa's icy shell and its deep ocean. Europa's surface is one of the most geologically active regions in our solar system, and the Moon's distinctive cracks, ridges, and tectonic features have captivated scientists for decades. Webb's observations of these surface features have provided new insights into the Moon's geological processes and how they might be linked to the ocean beneath. Europa's surface is covered by a thick layer of water ice, which is reshaped by geological activity. The icy shell is dynamic, continuously changing. Webb's infrared observations allowed scientists to study the surface in greater detail, highlighting how the icy crust interacts with the ocean below and providing evidence of ongoing tectonic and thermal activity. One of the features on Europa's surface is the vast network of long, linear cracks known as ridges. These ridges, often miles long and hundreds of meters wide, are believed to be the result of tectonic forces that stretch the ice crust. These stresses are likely driven by tidal flexing caused by Europa's orbit around Jupiter and its interactions with the other Galilean moons, Io, Ganymede, and Callisto. This stretching and compressing of Europa's surface causes the ice to crack and break, creating the ridges and faults that define much of the Moon's landscape. Webb's data provided detailed observations of these surface features, revealing their intricate patterns and offering insights into how Europa's ice shell might be responding to the forces acting on it from below. The ridges are evidence of the interaction between Europa's subsurface ocean and its icy shell. The stretching of the ice caused by tidal forces could allow water from the ocean beneath to seep through the cracks, creating new surface features. This process may explain some of the Moon's surface characteristics, such as the chaos terrains, regions where the surface appears to be broken up into blocks that have been rotated or displaced. Webb's observations showed that these chaotic regions are geologically active and may indicate material transfer between the ice shell and the ocean below. Webb's data captured thermal emissions coming from these surface features. The cracks and ridges showed areas of higher than expected temperature, indicating that these regions are being heated by geothermal activity beneath the ice. This localized heating is likely driven by the same tidal forces that cause the tectonic stretching of the ice, creating hotspots that could lead to the formation of cryovolcanoes, volcano-like features that erupt with icy materials instead of molten rock. The detection of these thermal anomalies supports the idea that Europa's surface is an active environment where the interaction between the surface and the subsurface ocean is ongoing. The discovery of thermal anomalies along Europa's surface provides further evidence of geothermal activity. Just as on Earth, geothermal energy could serve as a potential energy source for life forms that might exist in Europa's subsurface ocean. On Earth, life thrives around hydrothermal vents at the bottom of the ocean, where heat and minerals from the Earth's interior provide energy for ecosystems. Europa's surface features, especially the areas with elevated temperatures, suggest that similar environments could exist beneath the icy shell, where heat from the ocean's depths might support microbial life or other forms of life adapted to extreme conditions. Webb's observations also allowed scientists to study the composition of Europa's surface features in greater detail. By analyzing the infrared spectrum reflected off the Moon's ice, scientists detected a range of chemical compounds, including salts, sulfuric compounds, and organic molecules. These compounds suggest that the surface ice could be chemically rich and interact with the subsurface ocean. The presence of salts such as magnesium sulfate, sodium chloride, and sodium bicarbonate, points to the possibility that Europa's ocean might have a composition similar to Earth's oceans. The salts detected by Webb could help understand how Europa's ocean interacts with the icy shell. The presence of salts in Europa's ice might suggest that material from the ocean is being transferred to the surface through the cracks and ridges. When Europa's ocean is brought to the surface, the salt could preserve evidence of the ocean's composition, providing researchers with a chemical fingerprint that can be studied. Additionally, the salts could be involved in cryovolcanic activity, as heat beneath the ice causes water to rise to the surface, carrying the dissolved salts with it. This interaction between the ocean, ice, and surface could provide a key mechanism for chemical exchanges. Webb's observations of Europa's surface features could inform future missions. The upcoming Europa Clipper mission, scheduled to launch in the 2022, will fly by Europa multiple times, gathering detailed data about its surface, ocean, and subsurface composition. Webb's findings have already shaped the mission's scientific priorities, especially in identifying the most promising regions of Europa to investigate. By studying the thermal anomalies and surface compositions revealed by Webb, scientists will be able to direct Europa Clipper to regions where the interaction between the ice shell and the subsurface ocean is most pronounced. Webb's detection of thermal anomalies and surface features in regions where ridges and cracks are present could provide targets for the Clipper mission's instruments, which are designed to measure the composition of the ice, analyze the chemical signature of surface materials, and study the potential for plumes of water vapor to erupt from beneath the surface. The upcoming Clipper mission will build upon Webb's discoveries, taking a closer look at these surface features to determine how heat and material are transferred between the surface and the ocean below. Europa's surface features offer insights into the Moon's geological and chemical history. The cracks, ridges, and chaotic terrains are important for understanding the Moon's internal dynamics and how its ocean might sustain chemical processes. Webb's ability to capture the fine details of these features has added to the understanding of Europa. As scientists continue to analyze Webb's data and prepare for future missions, these surface features will remain a focus of exploration. The surface features of Europa are evidence of an ongoing dynamic process that connects the Moon's icy shell to its subsurface ocean. Webb's observations of cracks, ridges, and thermal anomalies have revealed a more active, geologically complex world. These findings provide information for future missions and contribute to our understanding of Europa's geologic and chemical activity beneath its ice. Europa versus Enceladus, the battle of the ice moons. As the James Webb Space Telescope pushes the boundaries of space exploration, one of the most fascinating aspects of its discoveries is the comparison between two of the most intriguing moons in our solar system, Europa and Enceladus. Both moons are icy worlds with subsurface oceans that have captured the imagination of scientists and astrobiologists alike. They represent two of the most promising places to search for extraterrestrial life, yet they are vastly different in many respects. Europa, orbiting Jupiter, and Enceladus, orbiting Saturn, share some key similarities, but their environments and the processes shaping their icy crusts offer contrasting challenges and opportunities for future exploration. Europa's surface is dominated by cracks, ridges, and chaotic terrains, shaped by tidal flexing and interactions with Jupiter's magnetosphere. Enceladus is known for its geysers that erupt plumes of water vapor and ice particles into space. Both moons harbour subsurface oceans, but the methods by which these oceans interact with the surface are different. Webb's findings regarding Europa's surface features allow for a comparison between the two moons and their potential for harboring life. Enceladus, with its active geysers, has been a focus of interest for astrobiologists. The Cassini spacecraft, which studied Saturn and its moons from 2004 to 2017, provided key data about Enceladus's water plumes. These plumes are connected to the moon's subsurface ocean, which is in contact with the rocky core of the moon. The eruption of these plumes has led to the discovery of organic molecules, salts, and simple compounds like carbon dioxide in the material from Enceladus's surface. This indicates that Enceladus's ocean may be capable of sustaining life. The plumes allow for sampling the ocean without drilling through the ice. Europa's ocean is sealed beneath a much thicker ice shell, making direct access to its waters difficult. Webb's infrared observations have provided insights into the thermal features and surface compositions of Europa, offering a better understanding of how the ice interacts with the subsurface ocean. Webb's detection of thermal anomalies and chemical compounds on Europa's surface suggests that heat is transferred from the ocean below, likely due to tidal heating caused by Jupiter's gravity. This process may enable Europa's ocean to remain warm enough to support life, similar to Enceladus's ocean. The major difference between the two moons lies in how their subsurface oceans communicate with the surface. Enceladus's plumes offer a direct connection between the ocean and space, allowing for chemical analysis of the ocean's composition. Webb's observations of Europa focus on how the subsurface ocean may exchange heat and material with the icy shell above, as evidenced by the detection of thermal anomalies and the composition of Europa's surface. Europa's ice shell, though thicker than Enceladus's, is still dynamic. Webb's ability to detect heat variations on Europa's surface indicates that the ice may be thinner in certain areas, allowing for greater heat transfer from the subsurface ocean. This finding suggests that Europa's surface may not be a complete barrier to material exchange between the ocean and space. Webb's observations have sparked interest in the possibility of cryovolcanic activity on Europa, which could provide a pathway to the subsurface. The comparison between Europa and Enceladus highlights the different radiation environments in which these moons exist. Europa, situated in the intense radiation environment of Jupiter's magnetosphere, is bombarded by high-energy particles. This radiation plays a role in the chemical processes on Europa's surface, including the formation of the oxygen-rich exosphere observed by Webb. Enceladus's orbit around Saturn places it outside of a strong magnetosphere, resulting in a less hostile radiation environment for life in its ocean. Both moons share a key characteristic: their potential to support microbial life beneath their icy shells. Enceladus's active plumes have provided evidence of organic molecules and water vapor, while Webb's observations of Europa's surface have offered new insights into the dynamics of its ocean and surface chemistry. Both moons are believed to have subsurface oceans kept liquid by tidal heating, a mechanism that could provide the necessary energy for life to survive. However, the accessibility of these oceans differs, with Enceladus offering a direct pathway to study its subsurface through its plumes, while Europa presents a more complex challenge for exploration. The upcoming Europa Clipper mission will study Europa's surface, ocean, and subsurface in greater detail. One of the key objectives of the mission is to gather data on the moon's surface features, chemical composition, and the dynamics of its ice shell. The mission will build on Webb's findings, particularly in understanding the thermal anomalies and surface features that may provide indirect evidence of the ocean's composition. In contrast, the Cassini mission's legacy remains significant in the study of Enceladus. Cassini's discovery of organic compounds and water vapor in the Moon's plumes provided key data about the composition of the subsurface ocean. With future missions like NASA's Dragonfly targeting Saturn's moon Titan, the comparison between Europa and Enceladus will continue to evolve. But both moons remain important targets for astrobiological research in the outer solar system. Europa's surface and subsurface have become a focus of scrutiny, with Webb's observations contributing to our understanding of its characteristics. Enceladus's active plumes provide a direct connection to its subsurface ocean, while Europa's icy shell presents a challenge, offering clues about the interactions between ice, water, and heat. The discoveries made by Webb and future missions like Europa Clipper will further refine our understanding of these moons. The exploration of Europa and Enceladus highlights the diversity of icy moons in our solar system and their subsurface oceans. Webb's observations have provided key insights into both moons, revealing the complexities of their surfaces and oceans. While Enceladus's plumes offer a direct look at its subsurface, Europa's icy shell presents challenges for exploration. The power of Webb. How the telescope changes space exploration. The James Webb Space Telescope's technological prowess has been particularly impactful in the study of icy moons like Europa and Enceladus, offering details about these celestial bodies' internal compositions, surface structures, and even potential for life. While the discoveries Webb is making in our corner of the solar system are groundbreaking, its true significance stretches far beyond that. The JWST's design and capabilities represent a significant advancement compared to its predecessor, the Hubble Space Telescope. The most noticeable difference is Webb's primary mirror, which spans 6.5 meters, about 21 feet in diameter, more than 2.5 times larger than Hubble's. This allows Webb to collect more light, which is essential for observing faint objects in deep space, from distant galaxies to exoplanets. The increased size of Webb's mirror, combined with its infrared capabilities, also makes it effective for observing objects like Europa within our solar system. What sets JWST apart is its infrared capability. Unlike Hubble, which primarily operates in visible and ultraviolet light, Webb observes in the infrared spectrum. This enables the telescope to study cooler objects that do not emit visible light, such as distant exoplanets, cold outer planets, and moons like Europa with their thick icy shells. Webb can examine the surface temperatures of Europa, detecting areas of heat variation that suggest subsurface activity. Europa, with its icy surface and subsurface ocean, has been a subject of study for scientists. Webb's observations have improved our understanding of how Europa's ice interacts with its ocean, revealing thermal anomalies that suggest active geological processes beneath the surface. Tidal forces, generated by Europa's orbit around Jupiter, cause stress on the icy crust, leading to cracks, ridges, and other surface features. Webb's ability to detect heat variations provides insight into how tidal flexing could transfer heat from the Moon's subsurface ocean to its surface, a process known as tidal heating. Europa's surface, a frozen shell of water ice, is challenging to study. The thick icy crust makes it difficult to access the subsurface, and until Webb's infrared observations, much of the activity beneath the surface remained unclear. Webb's sensitivity to infrared radiation allows scientists to detect subtle thermal emissions from cracks and ridges in the ice, identifying regions where geothermal heat is coming through the surface. These findings could indicate cryovolcanic activity, where water and other materials erupt from beneath the surface, providing potential pathways to the subsurface ocean. The ability to detect these heat signatures offers clues about Europa's internal dynamics, particularly its subsurface ocean's depth and composition. Webb's contributions extend beyond studying individual moons like Europa. The telescope has enhanced our ability to observe and analyze objects across the solar system. One of its missions is to examine the atmospheres of exoplanets, searching for signs of life or conditions that could support it. Webb's infrared instruments, such as the near-infrared camera and the mid-infrared instrument, allow for detailed analysis of an exoplanet's atmosphere. By examining the absorption patterns of light as it passes through an exoplanet's atmosphere, scientists can determine its chemical composition. Webb's ability to detect life-sustaining compounds extends beyond exoplanets. For moons like Europa and Enceladus, Webb's infrared observations have helped scientists identify key organic compounds on their surfaces. While we cannot directly sample Europa's subsurface ocean yet, Webb's infrared instruments provide important data about its chemical makeup. Europa's surface features, including salt deposits and organic materials, could help refine models of the moon's habitability. The JWST has already made significant contributions with its ability to observe objects farther than previous space telescopes. Its observations of distant galaxies and star-forming regions are providing new insights into the early universe. Webb can observe galaxies as they existed a few 100 million years after the Big Bang. By capturing the faint infrared light emitted by the first stars and galaxies, Webb is providing a clearer picture of how galaxies, stars, and planets formed. Webb's technological capabilities also impact the exploration of the outer solar system, as demonstrated with the study of Europa. The telescope's ability to detect thermal variations in the ice surface and analyze the chemical composition of its surface materials provides new pathways for understanding the dynamics of icy moons and distant planets. Webb's ability to measure the chemical signatures of water vapor, salts, and organic molecules on moons like Europa and Enceladus offers key insights into their characteristics. This level of detail helps astronomers identify promising areas for future exploration, such as those targeted by missions like the Europa Clipper, which will study Europa in greater detail. Another aspect of Webb's capabilities is its collaboration with other space missions and observatories. While Webb operates in the infrared, other telescopes, such as Hubble, provide complementary views in ultraviolet and visible wavelengths. Together, these instruments offer a more complete picture of distant worlds and help scientists understand their conditions in greater detail. The synergy between Webb and other telescopes enhances the scope of discoveries, increasing the value of combined knowledge from multiple missions. One of Webb's key roles in the future will be identifying exoplanets that could be candidates for the search for life beyond Earth. Webb's ability to observe exoplanet atmospheres in detail will allow scientists to prioritize which planets to study further. If Webb detects the right combination of elements and molecules, such as water, carbon dioxide, and methane, scientists will know where to focus the search for extraterrestrial life. As Webb continues to operate and expand our knowledge of the cosmos, its implications for space exploration are significant. The telescope has already begun to address questions about the building blocks of life, planet formation, and the conditions necessary for life. By providing data on these topics, Webb is helping pave the way for future missions that will further explore the mysteries of space. Beyond Europa, what Webb's technology means for other moons. While Europa has captured much of the scientific spotlight, the James Webb Space Telescope is poised to revolutionize our understanding of other moons in the solar system as well. Its extraordinary capabilities are not limited to Jupiter's icy moon. They extend to Saturn's moons, Neptune's Triton, and even smaller bodies in the outer solar system. Webb's ability to observe in infrared wavelengths, combined with its exceptional resolution and sensitivity, is enabling scientists to explore worlds that have long remained enigmatic. Each of these moons offers a unique opportunity to study geological activity, chemical composition, and potential habitability, and Webb is giving us the tools to unlock these secrets. Saturn's largest moon, Titan, is one of Webb's key targets. Titan has a dense atmosphere primarily composed of nitrogen, along with methane and ethane. Its surface is hidden under a thick orange haze, but Webb's infrared instruments can pierce this layer to reveal lakes, rivers, and seas of liquid hydrocarbons. Titan's environment is of particular interest due to its organic chemistry, which may offer insights into early Earth-like conditions. Observations from the Cassini mission had already provided detailed maps of Titan's surface and identified complex organic molecules, and Webb further adds by measuring surface temperatures, atmospheric composition, and seasonal changes. Webb also enables scientists to track methane cloud dynamics, analyze the composition of Titan's lakes, and study the possibility of subsurface oceans beneath its icy crust. Neptune's moon Triton benefits from Webb's advanced capabilities. Triton, captured by Neptune's gravity, has an unusual retrograde orbit and displays signs of geological activity. Voyager 2's flyby in 1989 revealed geysers of nitrogen gas erupting from Triton's surface, suggesting a dynamic interior despite its distance from the Sunday. Webb's infrared observations can detect heat anomalies on Triton's surface, allowing scientists to study active regions. Additionally, the telescope can analyze surface ices such as nitrogen, methane, and carbon monoxide, and assess the presence of organics, providing clues about Triton's internal structure. Saturn has several smaller moons, such as Enceladus, Mimas, and Dione, that fall within Webb's observational capabilities. Enceladus has already been extensively studied by the Cassini mission, but Webb can complement those findings by examining the composition of its icy surface, monitoring thermal activity, and analyzing organic molecules. Webb's ability to measure the infrared spectra of these moons allows scientists to track variations in surface composition that may indicate subsurface activity, even without plumes. Mimas, known for its enormous impact crater, Herschel, can be studied by Webb to provide detailed measurements of the thermal properties of the ice around the crater. Similarly, Dione, showing evidence of tectonic activity and fractures, can be studied with Webb to map temperature variations along these features and gain insights into the processes driving tectonic motion. Beyond the Saturnian system, the outer solar system holds moons that have largely escaped detailed study, and Webb is uniquely suited to fill that gap. Uranus's moons, including Miranda, Ariel, and Titania, have surfaces with complex terrains such as fault valleys, ridges, and resurfacing regions. These moons are cold and faint, making them difficult to study from Earth, but Webb's infrared sensitivity allows for detailed observation of their surfaces and compositions. By examining surface ices, organics, and thermal anomalies, scientists can infer geological activity, internal heating mechanisms, and the presence of subsurface oceans. Even small moons, previously considered too faint for detailed study, are now accessible with Webb, offering new insights into these distant bodies. Webb's observations are not limited to individual moons. The telescope can also study interactions between moons and their parent planets. Tidal forces from giant planets like Jupiter, Saturn, and Neptune generate heat within the moon's interiors, affecting surface geology and subsurface oceans. Webb's infrared imaging allows scientists to measure surface temperatures and detect regions of heat flow, providing insights into the strength and variability of tidal heating. By understanding how tidal forces shape the geologic and thermal environments of these moons, researchers can better assess their potential for future exploration. Another area where Webb is transforming our knowledge is the study of exogenic processes affecting moons. Many moons are bombarded by micrometeorites, radiation, and particles from their parent planet's magnetospheres, altering their surfaces and potentially affecting any subsurface oceans. For instance, Jupiter's radiation environment is harsh, which affects Europa, Ganymede, and Callisto differently. Webb can detect chemical signatures on these moons' surfaces, revealing the consequences of radiation-induced chemical processes and interactions with the space environment. On Saturn's moons, the lower radiation exposure allows scientists to isolate the effects of surface chemistry, geysers, and internal heating more clearly. Webb's contributions are critical in guiding future missions. The telescope's ability to map surface composition, detect heat anomalies, and monitor chemical signatures informs mission planners about which regions are most scientifically valuable. For instance, future missions to Titan, such as Dragonfly, benefit from Webb's detailed maps of the moon's surface and atmospheric conditions, allowing scientists to select landing sites with high scientific potential. Similarly, missions targeting Neptune's moons, or the Saturnian satellites, can use Webb's data to optimize exploration strategies, from flybys to potential landers or orbiters. Webb also enhances our understanding of moons in relation to broader planetary systems. Studying the composition, activity, and chemical evolution of moons provides clues about the formation and evolution of their parent planets. For instance, the presence of certain ices on moons can indicate the conditions under which they formed, such as the temperature and composition of the protoplanetary disk. Webb's ability to detect molecular signatures in the infrared spectrum allows scientists to compare moons across different planetary systems, revealing patterns that help understand the processes at work throughout the solar system. The telescope's advanced instruments also allow for time-domain studies, tracking changes in moon surfaces and atmospheres over time. Seasonal changes on Titan, plume activity on Enceladus, and thermal variations on Europa can all be monitored, providing scientists with insights into dynamic processes that were previously invisible. Webb can detect subtle differences in surface temperature over months and years, measure changes in atmospheric composition, and capture transient phenomena like geysers or cryovolcanic events. This long-term monitoring is essential for understanding the current state of these moons and the processes occurring on their surfaces and atmospheres. The James Webb Space Telescope extends humanity's reach across the solar system, transforming previously invisible objects into observable data. By providing detailed infrared imaging and spectroscopy, Webb allows scientists to study moons that were previously obscured by distance, ice, or atmospheric haze. Its observations of Saturn, Neptune, and Uranus's moons, as well as smaller satellites, provide crucial context for interpreting discoveries from Europa and Enceladus. Each moon observed adds valuable data, revealing the diversity of environments and interactions between surface, interior, and atmosphere. The telescope's ability to study these distant worlds in unprecedented detail enhances our understanding of the solar system and informs the exploration of moons and planets beyond our immediate neighborhood. Webb's technology expands the frontiers of space exploration far beyond Europa. Its ability to study the chemical, geological, and thermal characteristics of moons across the solar system is transforming planetary science. From Titan's lakes of hydrocarbons to Triton's nitrogen geysers, from the tectonic fractures of Uranian moons to the icy shells of Saturn's smaller satellites, Webb is providing critical data to understand these worlds in detail. The mystery of Europa's plumes, signs of subsurface activity. The study of Europa, one of Jupiter's largest moons, has captivated scientists for decades. Its thick ice crust, which covers a vast subsurface ocean, has long suggested the potential for life in its depths. But in recent years, a new feature of this frozen world has emerged as a focal point of research: its plumes. These geysers, which shoot water vapor, ice, and other materials into space, provide scientists with a unique opportunity to probe the moon's interior without having to drill through its thick, icy shell. The James Webb Space Telescope is now poised to explore these plumes in unprecedented detail, offering a glimpse into Europa's hidden world and potentially uncovering signs of subsurface activity that could be vital in the search for life. Europa's plumes were first detected by NASA's Galileo spacecraft in the late 1990 seconds, when it observed bursts of water vapor erupting from the moon's surface. These plumes, believed to originate from the subsurface ocean, periodically shoot jets of material high into space. The discovery of these plumes suggested that Europa's ocean might be more accessible than previously thought. Instead of drilling through the ice, scientists could collect samples of Europa's subsurface material directly from these geysers, providing valuable information about the moon's interior, its ocean's chemical composition, and the conditions beneath the ice. These eruptions are thought to be linked to the tidal forces exerted on Europa by Jupiter's immense gravity. As Europa orbits the gas giant, the gravitational pull causes the moon to flex, generating heat through a process called tidal heating. This heat drives the movement of water beneath the ice shell, creating pockets of liquid water and potentially forming the geysers that spew out from the surface. The plumes, composed primarily of water vapor, are believed to contain salts, organic molecules, and other compounds dissolved in Europa's subsurface ocean. While the plumes offer a glimpse into Europa's inner workings, studying them is challenging. The plumes are relatively small, erupting in brief bursts, and their composition is influenced by the conditions on the moon's surface and the dynamics of the eruptions. However, the advent of the JWST has opened new possibilities for studying these plumes with greater precision and detail. With its powerful infrared instruments, Webb can observe the plumes in a way that previous missions, including Galileo, could not. Webb's sensitivity to infrared light allows scientists to detect the heat signatures of the water vapor and ice particles in the plumes, revealing details about their composition, temperature, and the dynamics of the eruptions. One of the key aspects of Webb's observations will be its ability to detect the chemical composition of the material in the plumes. By analyzing the infrared light emitted by the plumes, Webb's instruments can identify specific molecules present, including water, salts, and organic compounds. This information is crucial for understanding the conditions on Europa. Organic molecules have been detected in the plumes, suggesting that Europa's ocean might contain the necessary ingredients for life. Furthermore, by studying the plumes, Webb can provide insight into the distribution of these compounds across the surface of the moon, helping to map out areas of interest for further study. The discovery of organic molecules in Europa's plumes suggests that the ocean beneath its ice might contain the necessary ingredients for life. While there is no direct evidence of life in the plumes, the presence of organic molecules and salts in the water suggests favorable conditions for life. Webb's ability to analyze these plumes in detail will provide valuable data for understanding the potential habitability of Europa's subsurface ocean. Webb's ability to study the plumes extends beyond their composition. The telescope's sensitivity to infrared radiation allows it to detect temperature variations within the plumes, revealing details about the dynamics of the eruptions. These temperature measurements could provide insight into the amount of heat generated by tidal forces, which plays a key role in determining the habitability of Europa's ocean. Tidal heating is believed to be responsible for maintaining the warmth of the ocean beneath Europa's ice shell, and Webb's observations could help quantify the extent of this heat and its effects on the Moon's interior. In addition to its observations of the plumes, Webb will provide new insights into the overall structure and dynamics of Europa's ice shell. The plumes are believed to be connected to cracks and fissures in the ice, and Webb's infrared imaging can help identify these surface features in greater detail. By studying the patterns of cracking and movement on Europa's surface, scientists can learn more about the thickness of the ice shell, the potential presence of liquid water beneath the surface, and how the Moon's ocean might interact with the icy crust. These surface features also offer clues about Europa's geological history, revealing how the Moon's ice shell has been shaped by tidal forces. Europa's plumes are not the only feature of the Moon that Webb will help scientists explore. The telescope's ability to observe Europa's surface in infrared wavelengths will also provide insights into the composition of the icy shell. Webb's instruments can detect the presence of various compounds on Europa's surface, including salts, sulfates, and organic molecules. This data is essential for understanding the composition of Europa's ocean and the processes that govern the interactions between the ocean and the ice shell. By studying the surface composition, scientists can also learn more about the chemical exchange between the surface and the ocean. In many ways, the combination of Webb's remote observations and the in-depth data provided by missions like Europa Clipper will complement each other, offering a comprehensive view of Europa's hidden ocean. Webb's contribution is important in the early stages of exploring Europa's plumes, helping scientists identify areas of interest for future missions and providing a framework for interpreting the findings from spacecraft that will visit Europa. The study of Europa's plumes also has broader implications for the search for life in the solar system. While Europa is one of the most promising candidates for extraterrestrial life, it is not the only place where plumes are found. Saturn's moon Enceladus, which also has a subsurface ocean, has been observed emitting geysers of water vapor, and other moons, such as Titan and Triton, may have subsurface oceans or active plumes. Webb's ability to study these plumes, both on Europa and on other moons, will be an important tool in understanding the distribution of habitable environments in our solar system. The plumes of Europa offer valuable clues to the Moon's subsurface environment, and Webb's observations of these eruptions will help advance our understanding of this icy moon. By studying the composition, temperature, and dynamics of the plumes, scientists will gain new insights into Europa's subsurface ocean and its potential for habitability. As Webb continues to explore the plumes of Europa and other moons in the outer solar system, we will gain a clearer picture of these distant worlds. The challenge of exploring Europa, a mission to the ice moon. Exploring this frozen moon, one of Jupiter's 4 largest satellites, presents a formidable challenge, requiring cutting-edge technology and precision engineering. With a surface entirely covered by thick ice and an ocean hidden miles beneath, sending a spacecraft to study Europa involves not only technological innovation, but also a careful balancing of scientific goals, logistics, and the harsh conditions of space. While space missions, such as NASA's Europa Clipper, are on the horizon, the complexities of such an endeavour are immense. Yet, the potential scientific rewards of a successful mission could reshape our understanding of the solar system's capacity for life. and provide vital clues about the broader nature of habitable environments. Europa's ice shell, estimated to be between 10 to 30 kilometers thick, is a significant barrier to exploring its subsurface ocean. This thick crust is one of the reasons why Europa is a challenging target for space exploration. The ice is an active surface, reshaped by the Moon's internal dynamics and the tidal forces exerted by Jupiter. The shell is fractured with large ridges and cracks, and the surface shows evidence of tectonic motion. While scientists have observed these geological features from afar, no spacecraft has yet landed on Europa's surface to take measurements or samples directly from the icy terrain. The primary goal of missions like NASA's Europa Clipper is to study the Moon's ice shell and subsurface ocean without landing. Europa Clipper, scheduled for launch in the 2022, will perform flybys, conducting detailed observations with instruments designed to analyze Europa's surface and subsurface from a distance. The spacecraft will carry tools such as a radar sounder to probe beneath the ice, a thermal imager to map surface temperatures, and a mass spectrometer to analyze Europa's atmosphere and plumes. Despite this collection of instruments, remotely analyzing such a dynamic environment presents significant challenges. Europa's radiation environment is a significant challenge. Being close to Jupiter, Europa is bombarded by high-energy particles from the planet's magnetosphere. These particles, mostly electrons and protons, create a harsh radiation environment. The radiation on Europa is up to 1,000 times higher than what astronauts experience in low Earth orbit. Protecting the spacecraft from this radiation is a significant engineering challenge. Europa Clipper will be equipped with a radiation shield to protect its electronics and instruments. The spacecraft will perform flybys instead of a prolonged orbit around Europa, reducing its time in the most intense radiation regions. Europa's surface presents additional challenges. The ice crust covering the Moon is highly reflective, making it difficult to observe with optical instruments. The surface is also often covered by thick layers of ice and snow, obscuring the underlying geology. The Europa Clipper mission will rely on radar, infrared, and thermal instruments to penetrate these layers and reveal the composition of the surface and the potential for an ocean beneath. The radar system is crucial as it will map the ice shell's thickness and identify areas where the ice is thinner, possibly providing pathways to Europa's hidden ocean. Europa's active surface features add to the complexity of the mission. The Moon's surface is reshaped by the movement of its ice shell and by tidal heating from the gravitational interaction with Jupiter. These dynamic features present challenges to study. For example, the plumes of water vapor are difficult to track and can vary in intensity depending on the Moon's orbital position. The Europa Clipper spacecraft will make multiple flybys, each providing new data on the Moon's surface features, geysers, and atmosphere. However, due to Europa's size and the short duration of the flybys, it can only study certain regions at a time. This requires scientists to carefully select the most scientifically valuable areas to explore during each pass. Europa's features make it an exciting target for future missions. In addition to Europa Clipper, other concepts are being considered to study the Moon in greater detail. One idea involves sending a lander or drill to Europa's surface. A lander could collect samples directly from the icy surface, analyze the composition of the ice, and measure temperatures at different depths. However, landing on Europa is complex. The surface is covered in jagged ridges and fractures, making it difficult to land safely. The spacecraft would need advanced navigation and landing technologies to ensure a successful descent. Drilling into Europa's ice to access the subsurface ocean would require a drill capable of penetrating up to 30 kilometers of ice, which presents significant technological challenges. The landing and drilling challenges are amplified by Europa's extreme surface temperatures. The average surface temperature is approximately negative 160 degrees Celsius or negative 260 degrees Fahrenheit, making it difficult to operate instruments or machinery on the surface. Materials used in spacecraft and landers must be able to withstand these temperatures without becoming brittle or malfunctioning. Any drill would also need to operate in these conditions without freezing or being damaged, while still collecting samples from deep beneath the ice. These technical challenges highlight the need for advanced spacecraft technology and a detailed understanding of Europa's surface conditions. Despite the obstacles, the rewards of exploring Europa are significant. Europa's subsurface ocean may contain the ingredients necessary for life, and understanding its composition and dynamics is essential for understanding potential habitability in the solar system. Studying Europa's icy crust and interior will provide insights into the geologic processes at work on icy moons, which could have broader implications for understanding moons around other gas giants and moons in other star systems. Scientists are developing new missions and technologies to explore Europa, while also utilizing data from other space telescopes, including the Hubble Space Telescope and the James Webb Space Telescope. Webb's infrared capabilities will complement future missions like Europa Clipper by providing detailed observations of the plumes, surface features, and thermal properties of Europa. These observations will help identify promising areas for future exploration and ensure that spacecraft are equipped with the right instruments for effective studies. In the coming years, the exploration of Europa will remain a challenging endeavour in planetary science. Europa's ocean, hidden beneath miles of ice, could offer clues about the origins of life and the processes that shape icy worlds. As technology develops to reach Europa's surface and study its ocean, we are advancing the capabilities of space exploration. The dynamic forces of Europa, tidal heating, and geological activity. When we think of Europa, we often imagine a frozen world of ice and water, an alien landscape of stark, desolate beauty. But beneath this frozen surface lies a complex history, one that has been shaped by forces both external and internal, from the gravitational tugs of Jupiter to the heat generated by tidal forces within the Moon itself. Europa's evolution is a story not just of ice, but of water, movement, and transformation, a history written in both the geology of its icy shell and the shifting dynamics of its subsurface ocean. The first clue to understanding Europa's evolution lies in its surface. Unlike many of the moons in the solar system, Europa's surface is not a simple, static feature. It is a mosaic of tectonic plates, ridges, and cracks that suggest a dynamic, ever-changing environment. Scientists believe that much of this activity is driven by tidal heating, a process that occurs because of Europa's orbit around Jupiter. As Europa orbits the gas giant, the immense gravitational forces exerted by Jupiter cause Europa's shape to flex and stretch, generating friction within its interior. This friction, in turn, heats up the Moon's icy shell and possibly its subsurface ocean, keeping the water liquid and enabling the dynamic geological processes we see today. Europa's surface features show signs of ice tectonics. Large ridges and cracks form as the icy shell stretches and breaks. These fractures indicate that the ice is constantly shifting in response to tidal forces. A prominent feature is the chaos terrain, where large blocks of ice are fractured and rotated. Studies from the Galileo spacecraft show that some chaos regions are up to 30 kilometers wide, with blocks several kilometers across, indicating significant ice mobility over time. Europa's surface history dates back billions of years to its formation. It likely began as a smaller body of ice and rock, accreting material as it orbited Jupiter. Tidal heating from Jupiter's gravity likely caused the Moon's interior to differentiate, with an ice shell forming on the surface. Beneath the ice, a liquid ocean, estimated to be up to 100 kilometers deep, may hold twice the volume of all Earth's oceans combined. This subsurface ocean is a key focus of the search for extraterrestrial life. Europa's subsurface ocean is in contact with the Moon's rocky mantle, creating conditions for geochemical activity. Hydrothermal vents, similar to Earth's ocean floors, may exist on Europa's seafloor, providing energy and nutrients. Tidal heating and frictional forces are thought to keep the water liquid and circulating. Models suggest the salinity of the ocean ranges between 2 and 5%, comparable to Earth's oceans, making it potentially suitable for extremophiles. Europa's ice shell is not just a passive layer, it is part of a highly active, dynamic system that interacts with the ocean beneath. The ice moves, cracks, and shifts, providing a pathway for material to exchange between the surface and the ocean below. For example, scientists believe that Europa's ice shell may allow for a type of geochemical cycling, where material from the subsurface ocean is transported to the surface and vice versa. This interaction could help sustain the chemical gradients that are essential for life, as well as provide key clues about the Moon's internal structure and the nature of its ocean. Some of the transported material may include salts, sulfates, and organic compounds, which Webb and previous telescopes have been detecting in surface spectroscopy data. The history of Europa's surface is not only shaped by the internal dynamics of the Moon itself, but also by the external forces acting upon it. The gravitational influence of Jupiter is a constant force on Europa, exerting immense tidal stresses on the Moon as it orbits the gas giant. These tidal forces stretch and compress Europa, creating the heat that drives geological activity and maintains the subsurface ocean in a liquid state. The nature of Europa's orbit, an eccentric path that causes the Moon to experience varying levels of stress over time, plays a significant role in shaping the Moon's surface features and its geological history. Observations of Europa's orbit suggest that its orbital eccentricity is maintained by a resonance with neighbouring moons Io and Ganymede, ensuring that tidal flexing, and thus internal heating, remains ongoing over billions of years. Europa's orbit is elliptical, unlike the orbits of other moons of Jupiter. As Europa moves closer to Jupiter, stronger gravitational forces cause greater stretching and heating of its interior. When farther from Jupiter, the forces weaken, reducing tidal heating. This variation in tidal forces has shaped Europa's surface, forming cracks, ridges, and chaos terrain. Some regions, such as the Lineae, are considered areas of repeated fracturing and resurfacing due to these orbital stresses. Europa's geological activity is also influenced by the interactions between its surface and Jupiter's powerful magnetosphere. As Europa orbits Jupiter, the Moon passes through the planet's magnetic field, which exerts forces on Europa's surface and atmosphere. This interaction creates auroras on Europa's surface, a phenomenon that is visible in the ultraviolet spectrum. These auroras, caused by the ionization of Europa's thin oxygen atmosphere, provide further evidence of the dynamic processes taking place on the Moon. Studying these auroras can help scientists understand the extent of Europa's magnetic field and the interaction between its ice shell and the magnetosphere, offering crucial insight into the Moon's internal structure. Variations in auroral intensity over time may also provide indirect clues about the movement of water within the subsurface ocean. Future missions, such as NASA's Europa Clipper, will help scientists understand the processes that have shaped Europa's surface and interior. The spacecraft will map the thickness of Europa's ice shell, study surface features, and analyze the composition of its ocean and atmosphere. These observations, combined with data from Earth's icy bodies, will provide further insight into the forces at work on Europa. Webb's infrared observations will also help identify thermal anomalies, indicating active regions and potential plume activity. Europa's evolution involves dynamic interactions between internal and external forces, including tidal heating, gravitational forces, and the interaction between Europa and Jupiter. The ice shell over the subsurface ocean reflects the Moon's complex history. Ongoing exploration of Europa, especially with advanced instruments like Webb, will continue to provide insights into its history and the potential for conditions conducive to life. Europa's ocean, investigating the potential for life beneath the ice. The search for life beyond Earth has long captivated humanity's imagination, and among the many celestial bodies that might hold clues to this profound question, Europa stands as one of the most intriguing. In the pursuit of this possibility, Europa has become a focal point for astrobiologists, planetary scientists, and space exploration agencies around the world. The potential for life on Europa is not just a matter of curiosity, but one that could change our understanding of life itself, its origins, its survival, and its potential to exist beyond Earth. The first key to understanding Europa's potential to support life lies in the composition of its subsurface ocean. The ocean is thought to be in contact with the Moon's rocky mantle, which would allow for geochemical reactions that could provide the necessary conditions for life. On Earth, life is sustained by hydrothermal vents on the ocean floor, where heat and chemicals from the Earth's interior create a suitable environment for microbes to thrive. Scientists speculate that similar hydrothermal activity could exist on Europa, where tidal heating from Jupiter's immense gravitational influence generates enough heat to keep the ocean beneath the icy crust liquid and potentially active. These underwater environments, if they exist on Europa, could be home to microbial life, much like the extremophiles on Earth that thrive in harsh environments. The presence of water is a crucial element in the search for life, but it's not enough on its own. For life to exist, the water must be chemically rich, with compounds that could provide the necessary building blocks for life forms. Europa's ocean, though shielded beneath miles of ice, may contain a variety of elements and compounds that could support life. Studies have suggested that the ocean could contain salts, organic molecules, and other essential ingredients. Salts like sodium chloride, or common table salt, and magnesium sulfate have been detected in the surface material of Europa, which suggests that similar compounds may exist in the ocean below. The combination of liquid water, organic molecules, and energy from tidal heating makes Europa an ideal candidate for astrobiological study. Recent observations by the Hubble Space Telescope and, more recently, the James Webb Space Telescope have provided clues about Europa's surface and atmosphere. Webb's ability to study Europa in infrared wavelengths has revealed insights into the composition of the Moon's surface and the potential for plumes of water vapor to escape into space. These plumes, detected in several locations on the surface, are thought to originate from the subsurface ocean, potentially offering a window into the Moon's interior. By analyzing the composition of these plumes, scientists can gain a better understanding of the ocean's chemical makeup and assess whether it could support life. One of the most exciting developments in the search for life on Europa is the detection of molecular oxygen in its atmosphere. While Europa's atmosphere is thin, composed primarily of oxygen, carbon dioxide, and water vapor, it is still significant in the context of astrobiology. Oxygen, as we know on Earth, is a key ingredient in the biochemistry of life. While Europa's oxygen is likely the result of radiation from Jupiter's powerful magnetosphere interacting with the Moon's surface, it still presents an interesting possibility. If the ocean beneath Europa's ice contains organic molecules and is capable of sustaining chemical reactions, the oxygen in the atmosphere might play a role in supporting microbial life, similar to how oxygen is used by microbes in Earth's oceans. The potential for life on Europa is not limited to the ocean beneath its icy shell. The surface of the Moon, while inhospitable to life as we know it, may hold important clues about the conditions below. Europa's surface is covered with cracks, ridges, and chaos terrain features that suggest the ice shell is dynamic and subject to constant movement. These surface features may represent areas where material from the subsurface ocean has been transported to the surface. If this material contains organic molecules, it could provide evidence of life for future missions to study. Europa's surface and the plumes that intermittently shoot water vapor into space are among the most promising places for scientists to look for signs of life. These plumes, which have been observed by both the Hubble Space Telescope and the Galileo spacecraft, may provide an easy way to access material from the subsurface ocean without having to drill through the thick ice shell. In fact, future missions to Europa could fly through these plumes, collecting samples from the Moon's interior. The potential for life on Europa raises many scientific questions about the conditions required for life to thrive. For example, can life survive in an ocean that is cut off from the sun, relying instead on energy from tidal heating and chemical processes? The discovery of life on Europa would provide critical insights into the range of environments in which life can exist and survive. The discovery of life on Europa would have significant implications for the search for life elsewhere in the solar system. Moons like Saturn's Enceladus and Neptune's Triton also harbour subsurface oceans, and the discovery of life on Europa could prompt further investigations of similar conditions on these moons. The study of subsurface oceans on icy moons is a growing field of astrobiology, with Europa playing a central role. The future of life detection on Europa lies in the hands of the next generation of space missions. Europa Clipper, set to launch in the coming years, will perform a detailed reconnaissance of the Moon, with an emphasis on understanding its potential habitability. By studying the ice shell, the ocean beneath, and the surface features, the mission aims to provide key insights into Europa's ability to support life. In addition, Webb's observations will continue to play a critical role in understanding Europa's atmosphere and the potential for plumes of water vapor to reveal the Moon's hidden secrets. The discovery of life on Europa may still be years or even decades away, but it is one of the most exciting aspects of current space exploration. Europa's role in the search for extraterrestrial life. In the vast expanse of the universe, Earth stands as the only known cradle of life. Yet, as we venture further into space, we are confronted with the tantalizing possibility that life may exist elsewhere, far beyond our own planet. For decades, astronomers, astrobiologists, and planetary scientists have turned their gaze toward moons and planets within our solar system and beyond, hoping to uncover signs of life or the potential for its existence. Among these worlds, Europa, the frozen moon of Jupiter, has emerged as one of the most promising candidates in the search for extraterrestrial life. Europa's subsurface ocean, the dynamic geological activity beneath its icy shell, and its potential for harboring life have all made it a central figure in the ongoing quest to understand whether life is a rare cosmic anomaly or a common feature throughout the universe. Europa's significance in the search for extraterrestrial life lies in its potential to support life and in what it represents about the conditions necessary for life to thrive. The discovery of microbial life or the chemical building blocks for life on Europa, would significantly enhance our understanding of how life might exist in environments where liquid water and sunlight are not readily available. One of the key reasons Europa holds such promise in the search for life is its sub-ice ocean. The presence of water is considered one of the fundamental prerequisites for life, as it serves as a solvent for biochemical reactions. Europa's ocean is estimated to be up to 100 kilometers deep, which is roughly twice the depth of Earth's oceans. This vast, liquid water reservoir is shielded from the harsh vacuum of space by a thick, icy shell, but it is still very much influenced by the surrounding environment, especially the gravitational forces exerted by Jupiter. Tidal flexing, the stretching and compressing of Europa's icy surface as it orbits Jupiter, generates heat within the Moon's interior, helping to maintain the ocean in a liquid state and allowing for the possibility of hydrothermal activity on the seafloor. These geothermal processes are thought to provide a source of energy that could sustain microbial life, much like the hydrothermal vents found deep in Earth's oceans. Europa's potential for harboring life is further supported by the presence of organic molecules detected on its surface and within its plumes. Organic compounds, such as methane and amino acids, are the basic building blocks of life as we know it. The detection of these molecules on Europa suggests that the Moon's ocean is chemically active and capable of supporting life forms. Although these molecules are not evidence of life on their own, their presence indicates that Europa's ocean contains the raw materials necessary for life's development. This discovery contributes to the search for extraterrestrial life, showing that the chemical ingredients for life may be present throughout the solar system. Europa's role in the search for life extends beyond its own potential to support life. The scientific insights gained from studying Europa's environment and ocean can inform the search for life on other icy moons, planets, and exoplanets. Moons like Saturn's Enceladus, Neptune's Triton, and even Pluto's Charon share similarities with Europa, such as subsurface oceans and geochemical activity. For example, Enceladus, another icy moon, has been found to have geysers that eject water vapor, organic compounds, and salts similar to the plumes observed on Europa. The exploration of Europa is not just about finding life in the traditional sense, microbial organisms or complex life forms. It is also about understanding the underlying conditions that could support life in environments vastly different from Earth. Europa's ocean, heated by tidal forces rather than sunlight, offers a valuable case study for how life could exist in other dark, distant environments. Many of the exoplanets discovered in recent years lie in the so-called habitable zone of their stars, where liquid water could potentially exist. However, these exoplanets are often too distant to explore in any meaningful way. Europa's ocean offers a closer model of a distant, dark world where life could survive. Europa's place in the search for extraterrestrial life has garnered the attention of space agencies around the world. NASA's Europa Clipper mission will be one of the most ambitious attempts to explore Europa's potential for life. One of its key objectives is to investigate the composition of Europa's ocean and assess its habitability. It will also study the Moon's surface features, including the cracks and ridges that may provide pathways for material exchange between the ocean and the surface. By gathering this data, Europa Clipper will help determine whether Europa's environment is capable of sustaining life, as well as provide critical information for planning future missions that could attempt to sample Europa's ocean or plumes. In addition to the Europa Clipper mission, the James Webb Space Telescope is poised to play a crucial role in the search for life on Europa. JWST's powerful infrared capabilities allow it to study the composition of Europa's surface, atmosphere, and plumes in greater detail than ever before. This information will be essential for understanding the chemical composition of Europa's ocean and whether it contains the necessary building blocks for life. Webb will also help scientists identify thermal anomalies on Europa's surface, potentially revealing areas of subsurface activity that could indicate hydrothermal vents or other sources of energy that could sustain life. Europa's role in the search for life extends beyond its potential to harbour life. Its study is part of a broader scientific effort to understand the distribution of life in the universe. Europa's ocean is not an isolated anomaly. It is part of a broader pattern of moons and planets that may harbour conditions conducive to life. As we look toward the future, the study of Europa and other icy moons in the solar system will continue to be a driving force in astrobiology and space exploration. The journey to answer the question of whether life exists beyond Earth is just beginning. Whether life is found on Europa or not, the discoveries made in the search will undoubtedly shape our understanding of life's resilience and its ability to exist in the most unexpected of places. The race to Europa, upcoming missions to investigate Webb's discovery, the excitement surrounding Europa's potential to harbour life and answer one of humanity's most profound questions, whether we are alone in the universe, has sparked an unprecedented race to explore this icy moon of Jupiter. The discovery of possible plumes and other intriguing data from instruments like the James Webb Space Telescope has only intensified the urgency. As technology advances and our understanding of Europa deepens, space agencies around the world are preparing to send missions to explore this fascinating world up close. The race to Europa is not just a competition of nations. It is a collaboration of humanity's best minds, all working toward unraveling the mysteries of one of the most tantalizing celestial bodies in the solar system. Europa's importance in the scientific community is immense. It represents a key place to search for extraterrestrial life, especially in environments vastly different from Earth. Over the past few decades, scientists have come to understand that life may exist in extreme environments, such as beneath the ice of Europa. The discovery of plumes, organic molecules, and tidal heating on Europa suggests that the moon may have all the necessary ingredients for life beneath its frozen surface. NASA's Europa Clipper mission is set to be the most significant mission to Europa in decades. The spacecraft will fly by Europa about 45 times over the course of its mission, allowing scientists to collect high-resolution data on the moon's surface features, including its cracks, ridges, and chaotic terrain. One of the most exciting aspects of the mission is its ability to analyze the plumes of water vapor that have been detected emanating from Europa's surface. These plumes, which may contain material from the subsurface ocean, provide a unique opportunity to sample the moon's interior without having to drill through miles of ice. The Europa Clipper mission will be equipped with a range of cutting-edge instruments, including an ice-penetrating radar system that will allow scientists to map the thickness of Europa's ice shell. This radar will provide a detailed view of the moon's internal structure, helping scientists determine if pockets of liquid water exist beneath the surface. By analyzing these internal features, scientists will be able to better understand how Europa's ocean interacts with its icy crust, and what implications this has for the potential habitability of the moon. In addition, the spacecraft will carry several spectrometers and cameras designed to study the composition of Europa's surface and atmosphere. By analyzing the chemical makeup of the surface ice, scientists can determine if organic molecules' key building blocks for life are present, further strengthening the possibility that Europa may harbor life beneath its icy surface. One of the most significant scientific instruments aboard Europa Clipper is its dust analyzer. This will allow the spacecraft to analyze particles in Europa's plumes, helping scientists understand the composition of the subsurface ocean and whether it contains the necessary ingredients for life. By collecting and analyzing material from the plumes, the mission can provide insights into the Moon's ocean chemistry without having to drill into the ice shell. The Europa Clipper mission's ability to conduct repeated flybys will allow it to gather a comprehensive data set that will be invaluable for understanding Europa's potential for life. In addition to the Europa Clipper mission, the European Space Agency, or ESA, is preparing for a mission called Jupiter Icy Moons Explorer, which is set to launch in the 2022 as well. While JUICE's primary focus is on Jupiter's moons, Ganymede, Callisto, and Europa, it will provide crucial data about Europa's environment. The spacecraft will carry a suite of instruments to study the Moon's ice-covered surface, as well as its magnetosphere, which plays a significant role in shaping Europa's atmosphere and surface features. JUICE will also study the interactions between Europa's ocean and Jupiter's magnetic field, which has a profound effect on the Moon's geology and potential for life. Although JUICE will not conduct flybys of Europa as closely as the Europa Clipper, its observations will complement those made by NASA's mission, providing a more holistic view of the Jovian system and the role Europa plays in it. The synergy between the Europa Clipper and JUICE missions is crucial in advancing our understanding of the Jovian system. Europa Clipper will provide detailed, high-resolution data on Europa's surface, plumes, and ocean, while JUICE will offer a broader perspective on the Moon's interactions with Jupiter and its magnetosphere. Together, these missions will provide a more comprehensive understanding of Europa's characteristics. While these two missions represent the most significant upcoming missions to Europa, the scientific community is also looking ahead to future endeavours that will build on the findings of Europa Clipper and JUICE. One of the key challenges of exploring Europa is accessing its subsurface ocean. The thick ice shell that covers it presents a significant obstacle, and new technologies will be required to overcome this challenge. As space agencies continue to develop their plans for exploring Europa, private space companies are also eyeing the Moon as a potential target for future missions. Companies like SpaceX, Blue Origin, and others are advancing technologies that could one day enable faster and more cost-effective missions to Europa and other outer solar system targets. SpaceX's Starship, for example, is a next-generation spacecraft designed to carry large payloads to distant destinations, including the outer planets. If successful, such private ventures could accelerate humanity's ability to reach Europa and other moons, enabling more frequent and detailed studies of these mysterious worlds. In addition to these current and upcoming missions, advances in telescopes and observatories will continue to play a crucial role in Europa's exploration. The James Webb Space Telescope, which has already made significant contributions to our understanding of Europa, will continue to provide valuable data throughout the coming years. JWST's powerful infrared capabilities allow it to study the chemical composition of Europa's surface and atmosphere with unprecedented precision. This will be essential in understanding the chemical makeup of Europa's ocean and determining whether the building blocks for life are present. As Webb also turns its gaze toward distant exoplanets, its insights will help refine our search for habitable environments beyond our solar system. Looking beyond the upcoming missions, the long-term goal is to drill into Europa's icy shell and directly sample its ocean. This would provide critical information about the conditions beneath the surface and their potential to support life. The race to Europa is about exploring the broader possibilities of life throughout the universe. If Europa harbours life, it may share similarities with other icy moons, such as Saturn's Enceladus. The discoveries made on Europa could provide a roadmap for future missions to other moons in our solar system. The future of space exploration. What's next for Webb? The James Webb Space Telescope has already marked a new era in space exploration, but its mission is far from over. While its groundbreaking discoveries regarding Jupiter's moon Europa have captured the world's attention, Webb is only beginning to unlock the secrets of the cosmos. The telescope's immense potential is not just limited to the exploration of moons and planets in our own solar system, but extends to far-flung galaxies, distant stars, and exoplanets in distant solar systems. As Webb's journey continues, it holds the key to answering some of the most profound questions humanity has ever posed about the universe. Questions about the origins of life, the fate of the cosmos, and the very nature of existence itself. Webb's design and capabilities make it a tool of unprecedented power, designed to observe the universe in infrared light with an unparalleled level of detail. Its ability to see through cosmic dust and its sensitivity to the faintest light allows it to study some of the most distant objects in the universe, objects that have never before been visible to human eyes. One of the primary goals of Webb's mission is to study the formation of stars and galaxies, particularly in the earliest moments of the universe's history. By observing the light from galaxies that formed billions of years ago, Webb will enable astronomers to peer back in time to the cosmic dawn, the period when the first stars and galaxies emerged after the Big Bang. Understanding how the first galaxies and stars formed will provide critical insights into the fundamental processes that shaped the cosmos. Webb's instruments, such as its near-infrared camera and mid-infrared instrument, are capable of detecting the faint infrared light emitted by distant galaxies. These instruments will allow scientists to observe these galaxies in detail, revealing how the earliest structures in the universe were born and evolved over time. The data Webb collects will help astronomers refine models of galaxy formation and stellar evolution. Beyond the study of the early universe, Webb will also play a transformative role in the search for exoplanets, planets orbiting stars outside our solar system. In the last 2 decades, the discovery of thousands of exoplanets has fundamentally changed our understanding of planetary systems. Many of these exoplanets are located in the habitable zone of their parent stars, where conditions might allow for the presence of liquid water, a key ingredient for life as we know it. Webb's ability to analyze the atmospheres of exoplanets will be a groundbreaking tool in the search for life beyond Earth. By studying the chemical composition of these distant worlds, Webb will be able to detect the presence of molecules like methane, water vapor, and carbon dioxide, potential biosignatures that could indicate the presence of life. The study of exoplanet atmospheres is a key part of Webb's mission, as it will allow scientists to determine whether these planets might be habitable. Webb's instruments, including the NIRCam and MIRI, will analyze the light that passes through the atmospheres of exoplanets during transits when the planet passes in front of its parent star. By studying the way light interacts with the planet's atmosphere, scientists can identify the chemical makeup of the air, the presence of clouds, and even the planet's weather patterns. This data will provide crucial information about the potential for life on these distant worlds and their habitability. However, Webb's scientific contributions are not limited to the study of stars, galaxies, and exoplanets. The telescope will also shed new light on the life cycles of stars. Webb's ability to observe stars in different stages of their evolution will provide critical insights into how stars are born, live, and die. By studying the birth of stars in dense molecular clouds, scientists will be able to learn more about the conditions that lead to stellar formation. Additionally, Webb will observe stars at the end of their lives, particularly those that are dying in spectacular explosions called supernovae. Understanding the life cycle of stars is essential for understanding the evolution of galaxies and the elements that make up the universe. Stars are the factories where elements like carbon, oxygen, and nitrogen are forged, and their death through supernova explosions distributes these elements throughout the galaxy, enriching the interstellar medium. In the coming years, Webb will also be integral in studying some of the most enigmatic objects in the universe, black holes. These regions of space-time have such intense gravitational fields that nothing, not even light, can escape. While black holes have been known to exist for decades, much remains unknown about their role in the evolution of galaxies. Webb's infrared capabilities will allow astronomers to study supermassive black holes at the centers of galaxies, investigating how these cosmic giants interact with their surroundings. Webb's ability to observe the regions near these black holes will help scientists understand how they grow, how they influence the galaxies they inhabit, and how they might even drive the formation of new stars and planetary systems. As significant as Webb's contributions are, its discoveries are not the only exciting developments in the world of space exploration. Webb's mission will serve as a launching pad for a new generation of space telescopes and missions that will build upon the knowledge it provides. One such mission is the Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2022. Roman will work in tandem with Webb, offering a wider field of view and faster survey capabilities. While Webb is focused on highly detailed observations, Roman will be able to conduct broad surveys of the universe, examining large-scale structures like galaxy clusters and mapping the distribution of dark energy. The combination of Webb's high-resolution observations and Roman's large-scale surveys will provide a more complete picture of the universe, enhancing our understanding of its structure, origins, and fate. Another key upcoming mission is the European Space Agency's Euclid mission, set to launch in the 2022. Euclid will study dark energy and dark matter, two of the most mysterious and elusive substances in the universe. Despite making up about 95% of the universe's total mass energy content, dark energy and dark matter remain largely invisible and poorly understood. Euclid's observations will complement Webb's research by providing crucial data on the large-scale structure of the universe, helping to map the distribution of dark matter and refine our understanding of the effects of dark energy. In the longer term, missions like NASA's Artemis program, which aims to return humans to the Moon, will lay the groundwork for future exploration of Mars and beyond. These missions are not just about sending astronauts to distant worlds. They are about developing the technology and knowledge needed to explore the farthest reaches of our solar system and beyond. Webb's findings will play a vital role in shaping the future of human exploration, providing the scientific foundation for understanding the environments we will encounter on other planets and moons. Webb is also paving the way for future missions to outer planets and their moons, such as Europa and Saturn's moon Enceladus. While the upcoming Europa Clipper mission, scheduled for launch in the 2022, will provide detailed data on Europa's surface, ocean, and potential for life, Webb's observations will continue to guide these future missions. Webb's infrared capabilities will provide critical data on the composition of Europa's surface and the presence of organic molecules, helping to prioritize future landing sites and sampling strategies. Scientists are considering next-generation telescopes and spacecraft that could extend Webb's reach even further. Concepts like the Large UV, Optical, IR Surveyor and the Habitable Exoplanet Observatory, or HABEX, are being developed as potential successors to Webb, aiming to study even fainter objects and distant exoplanets. The James Webb Space Telescope is not just a technological marvel. It is a symbol of humanity's unrelenting curiosity and desire to explore the cosmos. As we look to the future, Webb will continue to shape our understanding of the universe, uncovering new mysteries, inspiring new questions, and expanding the horizon of human knowledge. With each new discovery, we are reminded that the universe is vast, full of secrets waiting to be uncovered, and that the journey of exploration is just beginning.